Hello, guys. Can you hear me, guys?
Yeah, teacher, hi.
Hello, teacher.
Hello. Let's wait until 8:35 to begin, okay? Okay, I think we can begin. Today we're going to keep seeing about multi-component systems. So gas and vapor, or gas, vapor, and liquid equilibrium. Okay, to solve different kind of problems. Okay, so I will go back to the presentation. I will see it through from the beginning because I don't think everybody remembers everything we did last Monday. Okay, so so let me change the presentation and we begin. Okay. Okay, so multi-phase systems means that we have more than one phase: solid, liquid, liquid gas, whatever. That kind of thing, right? We saw what is a phase diagram. We saw what is a phase diagram and how this. Where is my note? Give me a second, that my tablet is not working. Okay, so we saw that these lines are equilibrium lines between solid and liquid, or gas, or vapor and liquid, and beyond the critical point. Beyond the critical point, you can condense a gas. That water, for example, can sublimate underneath here from solid to vapor, but at very low pressures and at very low temperatures. Okay, and then we saw at the flux diagram, right, that we a diagram where we have a vapor in point A, so we have a vapor at 20 degrees, and we have 3 millimeters of mercury, so they are vacuum, and then we will start raising the pressure until we get a liquid, right? We'll start seeing the equilibrium in the liquid phase. We'll start seeing the liquid phase here in A. We raise the pressure until we reach the equilibrium line of vapor and liquid in point B, And there we start seeing the formation of liquid until all the vapor goes to liquid, and then the pressure can keep rising again, right? At this point, keep rising the pressure. So we have a liquid, right? And we keep compressing until we reach to atmospheric pressure with a point C, right? And then what we want to do is to heat this system. So we start heating it until we reach to the equilibrium line of liquid and vapor again in point D. And in there we have a constant temperature until all the liquid changes to vapor, converts to vapor. So the liquid uses the energy to transform to vapor, and that's why the temperature doesn't rise. And when you have a vapor, you can go to point D, where you have well, a vapor overheated vapor, that's called, that has a higher temperature than the boiling temperature. Okay, so in this case, 130 Celsius, right? And then we saw how a diagram can, well, each component, for example, in this case, in the left, water, and in this case, CO2, carbon monoxide. We have, well, the values, the diagrams change, of course, because the interactions of the molecules. So here, for example, we can have at atmospheric pressure, this plot is in atmospheres, the pressure. So in carbon monoxide, we can have sublimation, right? That's what happens in concerts and so on. They have dry ice, that is carbon monoxide in solid state, and they heat it a little bit and it converts to vapor, right? And that's it. Okay. Other things is, well, the vapor pressure of components, right? For example, water has a low vapor pressure, but either way evaporates to atmospheric conditions, even if we don't have a boiling temperature, right? And acetone, perfumes, alcohol, gasolines, and so on, they have a high low vapor pressure. So the vapor pressure, what does mean is that some molecules have enough kinetic energy to go to the gas phase, right? So that amount of molecules, we can measure indirectly the kinetic energy through the vapor pressure. So if we have a high vapor pressure, we have high kinetic energy inside of the liquid. And if we close a system, well, it's going to reach an equilibrium where the air is going to be saturated with water vapor or acetone vapor or whatever you have, right? And when that happens, molecules from the liquid go to the gas phase, and molecules of the gas phase go to the liquid in the same rate, right? They have the same speed. So that's why it's reached an equilibrium, right? So the vapor pressure doesn't move at all again. Okay, so we saw a couple of things about the vapor pressure, as I just said. Of course, if the temperature is enough, the average kinetic energy of all the molecules, that's why it's the average, is going to be enough for to overcome the atmospheric pressure or the external pressure, and bubbles are going to start being formed on the solution. That is the boiling point, of course, the temperature of the boiling point. What else? So that's the definition of boiling temperature, right? When the vapor pressure of the solution is equal to the atmospheric pressure or the external pressure. That's why water boils at 100 degrees at sea level, but boils around 94 in Mexico City. That has around 0.77 atmospheres of pressure. Okay, so then we saw a couple of ways to estimate the vapor pressure. One is the Clausius-Clapeyron equation, when we need the enthalpy of vaporization and a constant for a gas, right? Temperature should be in absolute measurements, so Kelvin or Rankine, either one. And the pressure, well, depends on the system. Depends on how you have this constant, the V. The pressure is going to be in atmospheres or PCIs or whatever you want. That was Clausius. And this one, well, those are ready. And the ones that we're going to use more often is the Antoine equation. This Antoine equation, well, it's empirical fitting of the vapor pressure at different temperatures. So what you find doing a best fit scenario, mathematical equations, you obtain different coefficients A, B, and C. Right? Those coefficients change from component to component, and here is the temperature. Depending on the table that you find these values A, B, and C, the temperature you're going to be asked to put it in Celsius or Kelvins or Fahrenheit or ranking, depends on the table, right? For example, in the table that we have on the Felder, the B4 table, we are asked the temperature in Celsius, right? And the pressure that we find using this equation is going to be in millimeters of mercury. But that one can change too, depending on the table. It can give you in pascals or PCIs or whatever. Okay. So we still have to how to solve the system. The only thing you have to do is to raise T10, that is the inverse of the logarithm base 10, to all these numbers, right? To all this. Or in this case that we solved it at the beginning, we find a value, and that we raise 10 to that value. We cancel the logarithm base 10 in the side of the pressure, of the vapor pressure, and we find a vapor pressure, right? And that's it. Some important things that I told you is that you have to pay attention to the range where that formula, well, those coefficients A, B, and C work, right? If you are outside of that range, the errors are going to be very high, okay? More than 20%, 15%, 15%, so on, right? The Antoine equation is not the best way to estimate vapor pressure, but you have an error of around 5% or something like that. Okay, and we saw the last one. We saw the Cox chart. This Cox chart, what it is well, it's a plot of many lines with different components: ethane, propane, water, and so on, right? We have many components, and of course here we only have a couple of here, right? A couple of dozens. So how you read it is that you choose the temperature at where you are. Let's say 50 degrees. You go to the line. For example, this for N pentane, and then you go to the side, to the left, to the y-axis, and you measure the pressure, right? So in this case, let's say 0.32. In here, the pressure in this plot is in PCIs, right? Pounds per square inch. Okay, so that was how to estimate the vapor pressures, and that was it for last class, right? So now we are going to see how to use this information and other questions to solve problems like these ones. Okay. So the first thing to know is the degrees of freedom of a system, right? So in this case, for phases. So Gibbs, the same guy that did the Gibbs free energy, intelligent guy, did a thing to obtain the number of degrees of freedom or variables that we have to fix for solve our problem, right? So the first thing is to remember what is an intensive and an extensive variable, right? Intensive variables are variables that don't change with the amount of mass that you're measuring. So, for example, temperature is an intensive variable. It doesn't matter if you have 1,000 milliliters or 100 milliliters of water at 25 degrees is going to be at 25 degrees, right? So it doesn't change. Density is another, for example. Density, if you take the density of a block of steel, it's going to have the same density as if you take only one cubic centimeter of it, and so on, right? It doesn't depend on the mass. So there are many specific, many intensive variables, and the intensive variables are the variables that change with the amount of mass or of matter that we have. For example, volume. Volume changes all the time, but it depends on the amount of the component that we have. Other extensive, for example, the measurement or the length of a component of a system well, it changes depending on the amount of mass that that system has, and so on, right? The number of intensive variables that can be specified independently for a system and equilibrium is called the degrees of freedom of the system. It's more or less the same thing as the degrees of freedom in mass balance. So what do we have? The question that we have for the Gibbs phase rule is that F is the degrees of freedom, of course. That will be equal to 2 over plus C. C is the number of chemical species that we have in the system. If it's a pure component, well, 1. If we have a mixture, well, depends on the amount of components that we have on the mixture, minus uppercase pi, right? And that is the number of phases in a system at equilibrium. So if you only have one phase, like liquid phase, well, you choose 1. If you have, for example, a triple point, that you have 3 phases at the same time, well, 3, and so on, right? If you have a vapor liquid equilibrium, 2 phases, and so on. So let's obtain a couple of degrees of freedom. So we have 3 different systems here. The one in the left is water, liquid water. The one in the middle, in the middle is water, but at the triple point. So if you pay attention to the chart, or sorry, to the picture, you're going to see that you have ice in the tube, but at the same time you have gas over here, and at the same time you have liquid around, right? So you have the 3 phases of water at the same time. And the last example is the sparkling water. So in this case, we have water and carbon dioxide, and that has 2 phases, right? It has a type over here, say phases. So we have to see first how many components and how many phases, right? So if we have just pure water in liquid form, we have only 1 component and 1 phase, right? So if we calculate the degrees of freedom, we're going to have 2 plus C, that is the number of components, in this case 1, minus the number of phases that we have. So in this case, minus 1, because it's in liquid form, and we obtain 2 degrees of freedom, okay? So that means that we have to select 2 thermodynamic parameters to obtain all others. For example, could be temperature and pressure, for example, or temperature and composition, or so on. For the water at triple point, we have only 1 component, but we have 3 phases at the same time, right? So if we do the degrees of freedom calculation, we have 2 plus 1 minus plus 1 component minus 3 phases, and we have 0 degrees of freedom. That means that there is only one point in the plot, or one point in the system where that happens, right? We saw it on the phase diagram that it's only 1 point at one pressure and 1 temperature, right? You can't obtain a triple point outside of that particular temperature and pressure. Okay, so that's why it has 0 degrees of freedom, right? It's a fixed point. And the last one is sparkling water. So we have 2 components, water and carbon dioxide, sorry, and 2 phases, right? We have bubbles of the gas and liquid, right? So we have 2 components and 2 phases. So if we do that, we have 2 plus 2 minus 2, right? Components and phases, and we have 2 degrees of freedom. And again, to know the properties of this mixture, we need to give 2 values, right? So it could be the vapor pressure and the temperature and the pressure and the boiling point, and so on, many other combinations, right? Okay, any questions about the degrees of freedom, guys? If you have one, please unmute your microphone and let me know. Yep. Okay, so one way to relate the gas-liquid system is to use the Raoult's law. Okay, so the Raoult's law says the following: if a gas at a temperature T and a pressure P contains a saturated vapor whose mole fraction is Y, moles of vapor divided by moles of total gas, and if this vapor is the only species that would be condensed if the temperature were slightly lower, then the partial pressure of the vapor in the gas equals the pure component vapor pressure at the system temperature. Okay, so it's more convoluted that it really is. Okay, so for example, imagine that you have air and water. Well, air that has humidity, right? So water molecules inside of that gas. Okay, so a saturated vapor means that the system is full of water, right? You can't dissolve more water in the air. That's what it means. Yeah, and so it's in equilibrium, and it's of course the value of the vapor pressure, right? So if in this vapor, the only species that we have that can be condensed quickly is the water, right? Because nitrogen and oxygen condensate at minus 170 and minus 240 or something like that. So of course you can't condense nitrogen or oxygen, but you can condense water, right? Because water will be condensed well, at lower temperature, let's say 10 degrees, or depending on the properties that we're going to see. Okay, so that's what it means. So this equation is this, that the partial pressure of the component that can be condensed, Pi, it's going to be equal to the molar fraction in the gas phase, in the vapor phase of that component, times the pressure, the atmosphere, well, the total pressure of the system, or atmospheric pressure, and that will be equal to the vapor pressure of that substance at that system temperature. Okay, this is not a multiplication really, it's just that the pressure of the vapor, it's a function of T, right? So the vapor pressure is not going to change with the pressure, but just it's going to change with the temperature. Okay, depending only on the temperature of the vapor pressure. That is very important. Okay, so this is the Raoult's law with a single condensable species. Of course, if you have a more complex system where you have more than one component that can be condensed, this is a lot more complex, but it's not for this class, right? It's for thermodynamics and for other classes. Okay, so do you have any questions about this particular equation? This is going to be important in a few minutes. Okay, so let's continue then. Okay, so we're going to do a quick example, right? So it says composition of a saturated gas vapor system. It says air and liquid water are contained at equilibrium in a closed chamber at 75 Celsius and 716 millimeters of mercury, so atmospheric pressure. Calculate the molar composition of the gas phase. Okay, so that's what we have to do. Okay, so we have the Raoult's equation, right? We were saying air. We said that air, dry air, just oxygen and nitrogen, can't be condensed, but liquid water can. Well, water can, right? And if they're at equilibrium, it means that the air is completely full of water, right? It's saturated with water. Okay, so then we have to now look for, well, this equation, right? The Raoult's equation. We just said that because of the air and water, we can use the Raoult's law, right? And if we do that, we have, well, the equation, right? So we solve the Raoult's equation for the molar fraction in the gas phase of water. That will be equal to the vapor pressure of water at 75 degrees divided by the total pressure, right? So we have to find that value, right? We need the vapor pressure, okay? So because here we have, well, two known variables, right? We have the molar fraction of water, and we have the vapor pressure of water, okay? So water is one of the most studied component in the world, okay? So you have tables for any property that you want about water, and let's say something that is very important. The pressure of pure water, right? So it doesn't have, you have tables of pure water, right? So for example, in the filter, we have the table B3, that is the vapor pressure of water, right? So here we have the vapor pressure in millimeters of mercury versus the temperature in Celsius degrees, okay? Please always use, go and see the pressures and the temperatures, so the units of each variable, right? So you can do it correctly. So here we have the temperatures. In this column, we have the temperatures in changing in tenths, right? 50, 60, 70 degrees. And if you want the 50, for example, 53 degrees, you go to 50 and you go to 3, right? So 50 is 3, and the value will be 107.2. But in this case, we have 75. Okay, so 70 and 5. So we go to those two, and that tells us that the vapor pressure of water at 75 Celsius is 289.1 millimeters of mercury, right? So with that value, we can obtain the molar fraction of water in the air, in the gas phase, right? We need to do the relation between those 289 millimeters of mercury from the table and 760 millimeters of mercury from the problem, right? Atmospheric pressure. And that gives us that the molar fraction of water in that particular area at 75 degrees and 760 millimeters of mercury is 0.38, the molar fraction, right? That means that the molar fraction of dry air, right, that's going to assume it's one component, okay? We're going to treat it as one component, even if it's composed with water and oxygen and nitrogen. So, of course, that will be 1 minus the molar fraction of water, and this gives us 0.62 molar fraction of dry air, right? So, any questions of this particular example? That is a small point. Okay, so let's continue. A couple of things about the Raoult's equation. About this kind of system. A gas in equilibrium with a liquid must be saturated with the volatile component of that liquid. That means to be saturated, right? Well, and that means to be in equilibrium, because as we said in the diagram with the molecules going to the gas phase, if we have a closed system that is in equilibrium, well, the molecules of liquid that goes to gas and the molecules of gas that goes to liquid, they have the same speed, right? So it doesn't change. And then that gas is saturated, right? So it's full of the molecules of the volatile component. Then the partial pressure of a vapor at equilibrium in a gas mixture containing a single condensable component cannot exceed the vapor pressure of the pure component at the system temperature. This means that it doesn't matter if you, it means that the volatile component can have a higher vapor pressure than the pure component at that temperature. Okay, that's the highest amount, that's the saturated, right? It's the highest amount of that component in that system. So, for example, water, right? You only can have a certain amount of water in the air. After that, if you still keep adding water, it's only going to condense in the floor, right? You're going to obtain a pond of water, but the air is going to be saturated, and that's it. It can't go further. You can see it like, for example, when you do a solution in the lab with salt and water or sugar and water, there is a limit of the solubility of sugar in water, right? You can't dissolve any amount of sugar. There is a highest amount, right? A saturated solution of water and sugar. Well, it happens the same thing with gases, right? You have a high you have limit to that solution of water and air, for example, and that is, well, of course, the vapor pressure. Okay? Vapor present in a gas less than its saturated amount is referred to as a superheated vapor. Okay, so what this means is that if you have, for example, we saw that the vapor pressure at 75 degrees was 289, right? So if you have vapor pressure, you are at that temperature, but you are at the lower pressure, of the gas, you're going to have a superheated vapor, right? It means that to be saturated, you would need to lower the temperature a little bit. We're going to see an example in a few minutes. Okay, so what this means is that if the molar fraction times the pressure of the system or the or external pressure is lower than the vapor pressure at that temperature of the system, well, we're calling it a superheated vapor. Okay. And then, if a gas contains a single superheated vapor is cooled at a constant pressure, the temperature at which the vapor becomes saturated is referred to as a dew point of the gas. The dew point is called dew because, well, dew is like a fine drop of the liquid, right? So you have seen it many times with air and temperature. For example, if you are, let's say, January here in Mexico City, where the temperatures go around 5 degrees Celsius, you have a lot of water in the air, so you have a superheated vapor because you are not at vapor pressure, right, of water. But when the temperature is lower in the night, the temperature is going to reach the vapor pressure. The vapor pressure of the water dissolved in air is going to reach the pressure of the vapor at that temperature, and then water is going to start condensing, right? And you're going to see on the windows of your car, or on the windows of your home, or in the plants, you're going to start seeing drops of water, right? And it's the water that will condense because the temperature is lower than the amount of vapor, the amount of water that was in the vapor can have, right? Okay. So let's do an example, okay? This is a material balance around a condenser. So if you please would write down the questions, or take a picture or whatever you want. It says a stream of air at 100 Celsius and 5,260 millimeters of mercury contains 10% of water by volume. Okay. We have to do a couple of things. First, calculate the dew point and degrees of superheat of the air. 2, calculate the percentage of the vapor that condenses, and the final composition of the gas phase if the air is cooled to 80 Celsius at constant pressure. And the last one is calculate the percentage condensation of the final gas phase composition if, instead of being cooled, the air is compressed isothermally to 8,500 millimeters of mercury. Okay, so a couple of things. Well, the dew point we can calculate it through the temperature. Well, we can calculate it through the temperature and the concentration, right? One important thing here in the third one is it says isothermally, right? Isothermally means that the temperature is not going to change. Okay, so at constant temperature, is that what it means? Okay, so I'll give you a couple of minutes to grab the information that you need, and then we will continue to solve it. Okay?
Teacher, the presentation is already on Blackboard?
I'm not completely sure. If you want to, I can, while you do this, I can.
Okay, thank you.
We can do it. Let me wait a second. No. Uh-oh. I'm doing things that shouldn't be done. You still see the presentation, right?
Yes.
Yes.
Guys, I just uploaded it. It's on materiales, presentaciones. It's multi-phase systems if you want to download it.
Thank you, teacher.
Okay, so do you have the information that we need? Okay, so let me change to this one. Okay, so I'm going to solve it over here, right? Let's see. Okay, I copied the table that we're going to need. This is the V3 table on the folder. Okay, so that one you can grab it, of course, or you can see it in your computer if you want to. I just chose the part that we're going to need, right? Because of the temperatures that we have for that one. Okay, so the first point is to calculate the dew point, the degrees of superheating of the air. Right? So we start with the partial pressure of water, right? So that one should be the. Give me a second. So the partial pressure of water should be the molar fraction of water, right? Should be the molar fraction of water in the vapor, right? Times the pressure. Okay. Let me do the pen. Okay. So in this case, we know the molar fraction because we are assuming ideal gas, right? So if we know the percentage in volume, we know to the molar fraction of it. So the problem says that we have 10% of water by volume. So that means the molar fraction is 0.1 because volume can be related through the ideal gas equation, PV is equal to RT, to the number of moles, right? So it's the same thing. So we have 0.1 and times the pressure, right, that we have for the problem. So 5,260 millimeters of mercury, right? So that one, of course, it's only 526 millimeters of mercury. And then we can see at what temperature this pressure would be saturated, right? We can go to the table. That's why we have the table over there. So if you pay attention, we have the temperature at 100 Celsius in the problem, right at the beginning. So of course, at 100 Celsius, you should know that the vapor pressure is 760 millimeters of mercury. That's the boiling pressure of water, right? So should be the same as at 1 atmosphere. So we have 526 millimeters of mercury, right? So we go to the table and we look for that value. So if you go, you start lowering, and you say, okay, we have almost that value, 525.76 millimeters of mercury. Okay. So here for this problem, I'm not going to interpolate to see exactly what temperature should be, because it's very, very close to the 526 that we wanted. So we can read that the temperature is 90.0 degrees Celsius. Right? So that's our vapor. Well, that's our the pressure of water, the vapor pressure of water of at 90 degrees Celsius. It's equal to 526 millimeters of mercury. So that means that, well, that's the value that we wanted, right? So we calculate the degrees that this is superheated is, well, the temperature that we had at the beginning, 100 degrees, minus the temperature at which the vapor would be saturated, so 90 degrees, and this gives us 10 degrees of superheated, right? And the temperature of the dew point, well, if the partial pressure of water, 526, reaches the vapor pressure of water, that means that the system is saturated, and that would be the dew point, right? So the temperature of the dew point is equal to 90 degrees, okay? So anything lower than 90 degrees for this particular system would start condensing water, okay? So if you have, for example, 89, well, you will have a little bit of water condensed in the liquid form, right? So we have 10 degrees of superheat, and the dew point temperature is 90 degrees. Any questions on how did I reach to that particular point? Okay, well. So then in the second problem, it also calculate the percentage of the vapor that condenses and the final composition of the gas phase if the air is cooled to 80 degrees Celsius at constant pressure, right? So temperature equal to 80 degrees, and the pressure is still 5,260 millimeters of mercury, right? And the molar fraction, the initial molar fraction of water is still 0.1, right? So here we have to do a mass balance, right? So I'm going to draw the condenser, right? So here I'm going to put a box, right? And we're going to put air on it. Well, the air that we have, let's say that we have 100 moles, doesn't matter exactly how much, because we're going to calculate the number of moles of it, right? So we know that we have 0.1 of water and 0.9 of air, or like filter bullets is bone dry air, right? So completely dry air. Then if we have a condenser, we're going to have, of course, a certain amount of water, right? This is water. And the outlet is going to be the air plus a little, well, the bone dry air and water, right? So we're going to have a fraction of water that we don't know right now. And we're going to have, of course, the y minus y of water is going to be equal to the bone dry air, right? The fraction of it. We have the conditions: temperature equals to 80 Celsius, and pressure equal to 5,060 millimeters of mercury. And the last one is well, that of course, if we had the systems, this should be saturated with water, right? Because we determined that the dew point is 90 degrees, right? So anything lower than 90 degrees, of course, is going to, anything lower than 90 degrees will keep the air saturated, okay? So now we have our mass balance, okay? And we, of course, need to obtain the degrees of freedom, right? To see if this term can be solved. In this particular case, the unknown variables is N2 over here, N1 over here, and the fraction of water in the outlet, right? So we have three unknown variables, and then we subtract the equations, the mass balance equations, that we have only two components, right? Water and bone dry air, so we have two components. So that means if we only have this system, we have 1 degree of freedom, and then we are screwed, right? Because we can't solve this problem with 1 degree of freedom. So what do we do? Well, what we do is that we understand that the bone dry air is it's in a gas form and can't be condensed, changing a little bit of the temperature, but water is a condensable component in that mixture. And then we, of course, can use the Raoult's law, right? The Raoult's law, because we have a gas phase that has a condensable component. Okay, so here I'm going to subtract another one because we have the Raoult's law. and we have 0 degrees of freedom, right? So this one is from the Raoult's law. Okay. So now we know that we can solve this problem. Okay, so awesome. The Raoult's law, we're going to use it. We're going to use the Raoult's law to obtain this molar fraction of water in the outlet, right? That's the one we can obtain through the Raoult's law, right? So I'm going to do that up here. So Y of water, right, times the total pressure should be equal to the vapor pressure of water at the temperature, right? In this case, the temperature is 80 degrees. So because I forgot to put that table in this diagram, let me change to the book. This is the book, table B3, vapor pressure. Okay, so let me go to 80 degrees, right? Then we have here, it's a long table because we have many temperatures, and we reach to the 80, right? And we reach to 80 degrees, and here we can see that at 80 degrees Celsius, we have that the vapor pressure of water is 255.1 millimeters of mercury. So that's the value that we're going to use, of course. Right, so here we solve this equation for the molar fraction of water in the outlet, so we can put a 2 on it up here. This will be equal to the vapor pressure of water at 80 degrees, that we said it was 255.1, and that one divided by the total pressure of the system, that is 5,260 millimeters of mercury, that they just cancel, of course, and we obtain a fraction that should be 0.0675, right? This one, if you want the units, well, it's mole of water times per mole, right? That's the definition of. So we have the molar fraction of water in the outlet. Okay, so now we only have the mass balance equations, and we don't have any more degrees of freedom, so we can solve this problem, right? We're going to do a balance of the boundary error, right? So the inlet of dry air, should be equal to the outlet of dry air, right? So in this case, is 100 moles in the inlet times 0.9. That is the boundary air fraction, and that should be equal to the outlet. The outlet is N2, and then multiplied by 1 minus y, right? 1 minus y, that this y is the one from water, sorry. Okay, so we can solve N2 as 90, right? Divided by 1 minus 0.0675. And this gives us 96.5 moles, right? And then we have N2, right? We have N2, and we're only missing 1, right? So the easiest way to do it is, well, to do either the easiest way is to do a global balance, right? That the inlet in 100 moles is equal to N2 plus N1, that we have N2, so we can solve for N1, and that's it. Or we can do the mass balance of water. Of course, I'm going to do here the total balance, right? The total mass balance. So we said that 100 is equal to N1, that we don't know, is the water, plus N2, that is 96.5. And that, of course, gives us that N1 is equal to 100 minus 96.5, that is 3.5 moles of water that was condensed, right? And well, the percentage of condensation, it's from the water that we had, well, how much was condensed, right? So we condensed 3.5 moles of water, and we had at the beginning, we have in the air we had 0.1 times 100 moles, right? This, of course, if it's a percentage, should be times 100, and the 100s cancel each other, but this one is just 3.5 divided by 0.1, so the percentage of condensation is 35%. And that's it, right? So if you see, because we had a system with a condensable component, we could use the ideal gas, the Raoult's law equation, and with that one we'll obtain the mass balance, right? But we are not done just yet, right? We are missing the third point. The third point, it says that what happens. So what happens if we raise the pressure instead of the temperature, right? So it says, the problem says exactly calculate the percentage condensation and the final gas phase composition if instead of being cooled, there is compressed isothermally to 8,500 millimeters of mercury, right? So that one, we have to do something similar, right? So we know that at the beginning, we have.
Teacher, could you return for a moment to the previous page, please?
Okay. Find my mouse.
Thank you.
Okay. Okay, so we know at the beginning of this problem at 100 degrees and at a pressure of 1,250 millimeters of mercury, we knew that this system was superheated, right? So that means that the fraction of water times the pressure was lower than the vapor pressure of water, right? At that temperature. That's what it means at 100 degrees, right? So we know that for this system to condense, this should transfer to an equality, right? An equation with an equal, right? We have to do this, right? Go from the superheated to the condition where these values are equal, that is the saturation equilibrium, right? So we can calculate what would be the pressure of saturation, right? This pressure of saturation, because we can't change the value of the amount of water, the fraction, and we have a isothermal process, right? So the pressure of water at 100 degrees, well, it's not going to change, of course. It's going to be 760, right? So what we want to solve is P in this case. And I'm going to add a saturation, right? When this system is going to get saturated. So the vapor pressure of water at 100 degrees is 760 millimeters of mercury. And we divide that by the molar fraction of water, that is 0.1. That was a data. So this is 7,300 millimeters of mercury. So we know that if the pressure is higher than this 7,600 millimeters of mercury, then the system is going to condense, right? So we know that that's true because we're going to raise the pressure to 8,500. Okay, so we know that we're going to have condensation, right? So again, we have our system. Okay, so N1 is the mole of water, and here we have the outlet. Let's sign N2. Here we have Y, that is the moles of water. And we have 1 minus Y, that is the dry air. And we have the temperature at 100 degrees and the pressure at 8,500 millimeters of mercury, right? That's the data that we have. And here we have, let's say, 100 moles, 0.1 water, 0.9 bone dry air. Okay, So again, we knew the degrees of freedom of this problem already. Is 1 without taking into consideration the Raoult's law, but as we have the Raoult's law, we have 0 degrees of freedom. And that means that we can solve this problem, right? So the first thing is that we can obtain, again, the molar fraction of water at the outlet, okay? And we do the same equation in this case, so Y of water is equal to the vapor pressure of water at 100 degrees. That hasn't changed because this is a mesothermal process, and that divided by the total pressure that we raised to 800 millimeters of mercury. And this, of course, the vapor pressure of water at 100 degrees, it's 160 millimeters of mercury, so 1 atmosphere divided by the total pressure, right? And this gives us that the the fraction of water for this particular system should be 0.0894. Right? So now we can do again the bone dryer balance. Again, what it gets in, it has to get out, so 100 moles times 0.9. This should be equal to 1 minus y that we have 0.0894. So that M2 is equal to 98.8 moles. And with that one, we can obtain, of course, with the total balance, we can obtain that 100 is equal to H2 plus 98.8 moles. And this gives us that N2 is equal to 1.2 moles of water. And again, the percentage of condensation is equal to the moles of liquid water, that is the 1.2 moles of water, divided by the amount of moles at the beginning, that is 0.1 times 100, and this to be a percentage should be 100 of the units, and this is 12% condensation rate. So if you compare the two values, the one in the previous page that we obtained as 35% of condensation, and the one that we obtained just right now, that is 12% of condensation, you can see that, for example, the condensed water is a lot easier to lower the temperature instead of raising the pressure, right? Going to that amount of pressure, 8,500 millimeters of mercury, is very difficult. You need a special container and so on to lower the temperature. You need very expensive or specific things. Okay, so that's the way we can use the Raoult's law. I don't know if you have any questions about this problem, any of the the 3 points that we saw. Yep. Okay.
Yes, teacher, I don't understand very well the pressure saturate.
Okay. This value that we obtained here as that one? This one?
Yeah, yes.
Okay, so that means that we know that at the conditions that we had in the problem, 100 Celsius and 5,260 millimeters of mercury, the pressure, the partial pressure of water, so 0.1 times the pressure, 5,260 millimeters of mercury, it's lower than the vapor pressure of water at 100 degrees, right? So if we know that, because at 100 degrees is 760, we know that this vapor is superheated, okay? So to obtain the saturation pressure at which this fraction of water, the 0.1 fraction of water, would be equal to the vapor pressure of water at 100 degrees, we need to do inequality. Well, we need to have these two terms equal, right? the partial pressure of water should be equal to the vapor pressure of water at 100 degrees. So that's what we are solving, right? We are solving at pressure at which the water will start condensing. Okay, so
Okay.
yep.
Thank you. Yeah.
Okay. Any other questions, guys? Okay. So let's continue then to the presentation. So we solved this question, this example already. Okay, so a couple of things, important equations that we're going to be using. I'm going to define what they mean. Okay, so the relative saturation or relative humidity, it's a relation of how much. Okay, let's say that, for example, what is the percentage of saturation? Okay, so the relative saturation means how close we are from the saturation of the system. Okay, this is the value that the Weather Channel reports, right? That says we have a 55% of humidity. They just say humidity, but they mean relative humidity. So that what it means is that the air contains 55% of the water that could contain. Okay, that could be dissolved in the air. Okay, so we are 45% from saturation. Okay? So the formula to calculate that is the partial pressure of the component, let's say water, for the example that I'm giving, the partial pressure of water divided by the vapor pressure of water at that temperature times 100. So you see it's a relation of the partial pressure of water and how close is to the saturation, right? So that's why it's called relative humidity. Okay? Relative humidity, of course, changes with the temperature, right? Because vapor pressure changes with the temperature. Okay. Then we have what is called a molar saturation or molar humidity. Okay, where you can find any of these two terms, right? SM means molar saturation, HM means molar humidity. Okay, so any of those is not a multiplication. It's the same way here in the relative saturation or relative humidity. Okay, so in this case, what relates is the amount of moles of vapor, right? And the moles of vapor of free dry air gas. So in the example of water, in the case of the example that we just saw, would be the pressure, the total pressure, well, the total pressure, and the minus the partial pressure of the condensable component, in this case, water, for example. Okay, so the molar humidity tells you how many moles of vapor you have, of vapor, of water vapor in this case, divided by the total amount of moles of dry air, right? That one is not used so much, but it's a good way. It's good to have it. Then we have the absolute saturation. Okay, the absolute saturation, that it's either absolute saturation SA or it's absolute humidity HA. Either way, what it relates is the mass of vapor. The mass of vapor of the condensable component divided by the mass of dry air, of dry gas, because these equations work for any mixture of a dry gas with a condensable component. Okay, in the case of air, of atmospheric air, we have the mass of vapor is the mass of water that it's dissolved in the gas. And the mass of gas, well, it's the amount of gas without any water, right? So how the way we calculate the mass is using the molar mass of water in this case, or the molar mass of acetone, or the molar mass of water, right? Depends on the component, and the partial pressure. So the partial pressure of the condensable component times the molar mass of that component. If you remember, the partial pressure is it's equivalent to the molar fraction of it. Okay, so it's the same thing. The partial pressure, okay, times the molar mass, and then the dry gas. Well, we subtract from the total pressure the pressure of the condensable vapor, and we multiply by the molar mass of the dry gas, whatever it is. Okay, for water, 18 grams per mole in the molar mass, and for dry air is 28.86, if I remember correctly. Okay. And the last one is the percentage of saturation, SP, or percentage of humidity. Okay. So this what relates is how humid is the system. So it compares the molar humidity, SM, with the molar humidity, assuming that we have a saturated system. That's why it has the asterisk on it, times 100. So if we substitute this formula, the formula of the molar saturation, one over here, we substitute it over here, that's what it gives us, right? Only taking into consideration that we're having the vapor pressure or the saturation pressure of the condensable system, of the condensable component, and the vapor pressure and the partial pressure of the condensable component too, and that times 100. Okay, so these equations are important because many times in a system we can measure property in one way and not in another. Okay, so we have different way of relating these conditions or these variables. Okay, so another exercise to use these equations that we just saw. So it says humid air at 75 degrees Celsius and 1.1 bar, and 30% of relative humidity is fed into a process unit at a rate of 1,000 cubic meters per hour. Determine the molar flow rates of water, dry air, and oxygen entering the process. Second, the molar humidity, absolute humidity, and percentage of humidity of the air. And 3, the dew point. Okay, so we have to do all that. So let me change to the other software so we can do it. And let me add it. Okay. So,
can I see the problem, please, so I can copy it?
Oh, yes, okay. Let me know when you're done.
Thank you, teacher.
Okay. I'm going to put these equations over here so we can use them for the problem. Let me erase all these things. Okay. So the first part of the problem tells us that we need to determine the molar flow rate of water, dry air, and oxygen entering the unit, right? And the conditions that we have is that we have 75. So we have the temperature. So this is 1. So we have the temperature that is 75 Celsius. The pressure that is 1.1 bar. And we have the relative humidity. Relative humidity of 30%, right? That's the information that we have. So we go to, for example, if we go to here and we see the relative humidity. The equation is the partial pressure divided by the vapor pressure times 100, right? Okay. So we have that. It's equal to the partial pressure, in this case water, because it's a condensable, divided by the vapor pressure of water times 100, right? We have 30 for the relative humidity, and we can have the vapor pressure of water at 75 degrees, right? because we have a table for it. So we go to the table and we look for 75. Here we have it. 75 is this value, right? 70, and then we go to the 5, 289.1. Right? So we go to the problem, and we solve this equation for the the pressure of the partial pressure of water, right? So we will have we're going to have the relative humidity times the relative pressure of water at 75 degrees divided by 100, and this one is 30 times the relative pressure that we said it was 289.1, and divided by 100, right? So the partial pressure of water should be 86.7 millimeters of mercury, right? Remember that this value over here is from table B3, right? For the Felder. Okay, so we now have P, right? And we know that the molar fraction of water times the pressure is equal to the partial pressure, right, of water. So we can solve the molar fraction as the partial pressure of water divided by the total pressure. And that, of course, means that, oh, okay, sorry, we have to convert this value because we have millimeters of mercury, right? So this one is 1 bar, it's equal to 716 millimeters of mercury. It should be 8 to 5 millimeters of mercury. Okay, so we should substitute the data, 86.7 millimeters of mercury divided by 85 millimeters of mercury, and that gives us the position of the water as 0.105, right? So then we have the fraction of water, and of course then we can obtain the fraction of air, right? Okay, so that's the third part, the first part, and then we have to convert. It's telling us that we have a volume, a flow rate of 1,000 cubic meters per hour, right? Of this component, right? So we can obtain with using the ideal gas equation, we can obtain the molar flow, right? We have PP is equal to nRT, right? And we solve for N, so we have PV over RT, right? And we have all the conditions, right? We have T, we have B, we have P, we have R, right? So we substitute the data. The data that we have 1,000 cubic meters per hour times the pressure, that is 1.1 bar. And R in those units, it's 0.0831 cubic meters per bar divided by Kelvin mole, sorry, kilomole. And that's it, right? Sorry, missing the temperature. And the temperature is 35 degrees. 75 plus 273.15, and that gives us that the molar flow rate should be 38.0 kilomoles per hour, right? So now we can obtain, of course, the amount of moles of water because we have the molar fraction of water. And
Sure, I have a doubt.
Yes.
How did you convert 1.1 bar to milligrams of mercury?
It's over here. It's in the top of the screen. Is the relation.
Yeah, okay. Thank you.
So now to obtain the number of moles of water in the feed, we have the molar fraction that we calculated through the partial pressure. So we have that the number of moles of water is 3.99 moles of water per hour, and of course we can obtain the number of moles of bone dry air. That would be equal to 38 minus 3.99. And we're going to leave it as 34.3 moles of bone dry air. Okay, so that one, we solved the first one. Well, and it's telling us that we need the amount of moles of oxygen too, right? So the moles of oxygen, we know that the moles of oxygen will be related to the moles of bone dry air, right? And we have for each mole of bone dry air, we have 0.21 moles of oxygen. So that gives us that the number of moles of oxygen is 7.14 moles of oxygen per hour, right? Bone dry air was 34.01 times 0.21. Okay, so that solves the first part of the problem. Obtaining the oxygen, of course, is important if you're going to use that air for something like a reaction for a combustion or something like that. Okay. So then the second point is asking us for, remember, the second point is asking us for the molar humidity, absolute humidity, and percentage humidity of the air. So it's just substituting different equations, right? So the absolute humidity, HA will be the total number of moles of water. So in this case, sorry, I have something that is incorrect over here. Okay, so this is the number of moles of water divided by the number of moles of dry air, right? So we have 3.99 divided by 34.01, right? And that, let's go to the formula. HA is over here, right? So the mass of vapor divided by the mass of dry air. So that's it, right? We have to multiply it by the molar mass, that in this case is 18. This is in kilomoles. Moles. Yeah, so moles to kilograms per kilomole. The relation is going to stand, and divided by the molar mass of air, that we're going to say that it's 29 kilograms per kilomole. Okay, so this would give us that we have 0.0726 kilograms of water per kilogram of bone dry air. Okay, so that's the absolute humidity. Then we need to calculate the molar humidity. Sorry, the molar humidity. The molar humidity is over here, HM. So we need the partial pressures, the partial pressures of the gas. So HM is equal to PI over P minus PI. Okay, so this one PI, we have it. We have it here over here. The water is 86.7. So 86.7 divided by the total pressure, that is 825 millimeters mercury minus 867. This should be 0. Sorry, let me do the calculation. I don't have it over here. This is 86 divided by 825 minus 86.7. So that gives us 0.1165. Sorry, 65, right? We're for the that's the model humidity, absolute humidity, and percentage of humidity of the air, right? The percentage humidity of air, if you see the equation underneath, the humidity percentage of air, we need the molar saturation and the molar saturation using the vapor pressure, right? So we have to obtain that one too. Okay, so we know we have that value already because we have it here from table B3. So HM of the vapor pressure, right? Using the vapor pressure, and well, it's the same equation, only changing the values. It's going to be EI, the vapor pressure, the total pressure minus the saturation pressure of it. So in this case, 289.1 divided by the total pressure, that is 825 minus 289.1 again. And that one gives us, I think, 0.539. Okay. And the last one is the partial humidity. This one would be HM divided by HM of saturation times 100. So this, if we substitute the data that we have, it's going to be 0.1165, 0.539 times 100, and that should give us 21.7% of partial humidity, right? And we are done with time, but we are only missing one calculation. That is for the third point. The third point is telling us that we need to calculate the dew point. Okay? So for to calculate the dew point, we need the partial pressure of water, that we have it already, right? Partial pressure of water was 86.7 milliliters of mercury. And this to obtain the temperature, we have to equal it to the vapor pressure of water at the temperature of the dew point. Okay, so we go to table B3 and we look for that value, 87. So we're looking for 87, and if you have here, wait a second, what happened there? Okay, so we have it, right? We have the value that we wanted, that is around 86.7. So 86.7 is exactly this value here. And that one, if we measure it, is 48.7 Celsius, right? 48.7 Celsius. So the temperature of the dew point is 48.7 Celsius. And that's it. We used all the regions, all the values that we had, and we finished the problem. So I don't know if you have any questions about this problem. In this particular problem, is just the use of equations, right? You need to know of course the values of what the equations for each term that we want to calculate, and well, to see how we can obtain that information, right? For example, for the vapor pressure or the partial pressure and so on. So I don't know if you have any doubts. Good. Okay, so it's 9:85, so we finished the class for the day. That's it. See you on Monday. Have a good weekend.
Good teacher, the same to you.
Thank you, teacher. See you.
Thank you.
Thank you, teacher.
Thank you.
You're welcome. See you guys.
Teacher, for when it's the project?
Sorry. Yes, I will send you, because I'm already logged out. I will send you a email. But for next Thursday, we'll have the second stage, and the final stage is for the last day of class, so the 20th of November. Yep. Okay. See you guys.
See you, teacher.